Okay, hi guys, so in this lecture we'll be discussing on liquefaction of real gas. So let's get started. Liquefaction of real gas. Okay, so let's say we have a graph between P and V. Let me make it a bigger graph. So let's say I'm making various nature of the graph between P and V. And finally this one. Okay, so let's say it happens at temperature T1, where this is a gaseous phase, this is liquid or gas, and this is a liquid phase. So T1, T2 and T3, and this is the, we'll come to that later. So let's say in this case temperature T3 was more than T2, which was more than T1. Okay, so whenever the temperature becomes T3, we call it TC, which is nothing but the critical temperature of the gas. Okay, so let's say we define some points here, A, B, and let's say C. So at point A we can see that liquefaction commences or starts. Liquefaction commences. Okay, at point B we can say that liquefaction is over. At point C we can see that both phases, which is liquid and gaseous phase, are in equilibrium. Or rather, let's say before point C, let's say between point A and B, we can say that both phases, which is liquid and gas, are in equilibrium. Okay, and between point B to C we can say that negligible change in volume of liquid. Okay, and let's say we also have this point X. So at point X we can say that both liquid and gaseous phase are indistinguishable. Both phases, which is liquid and solid, liquid and gas, beg your pardon, liquid and gas are indistinguishable. Okay, and the temperature at which this happens is critical temperature. And let's say we now have another temperature T4. So about above critical temperature, real gas is called supercritical fluid, and above this the liquefaction is not possible. Okay, So critical temperature in a way is the maximum temperature at which the gas can be liquefied, or you can liquefy a real gas, or it is the maximum temperature at which liquefaction of a real gas is possible by applying certain amount of pressure. And above critical temperature we cannot liquefy a real gas. So let's say I mentioned earlier about this graph, uh, in which I told that we will discuss it later. So now we are discussing it, that above critical temperature, which is T4, the liquefaction of gas is not possible, and this would rather be just the gaseous form of the real gas. Okay, and all these graphs are actually isotherms. Okay, so they are at constant, they are at, all the graphs are at constant temperature, all the respective graphs rather are at constant temperature, that T1 is the same temperature throughout the liquid phase and the gaseous phase, similarly for T2, similarly for T3, similarly for T4. So these are isotherms of real gas. And at T4 what happens is, and at T4 this is supercritical fluid. Supercritical fluid. Okay, so we can write that above Tc, which was T4 in our case, real gas is called supercritical fluid. Okay, or in a way liquidation or liquefaction of real gas is not possible after Tc. Okay, so now let's look at more notes on critical temperature, which is Tc. So this is the maximum temperature at which we can liquefy a real gas. Or maximum temperature at which liquefaction of real gas is possible by applying pressure. Okay, and above critical temperature we cannot liquefy a real gas. Okay, next let's discuss critical pressure. Okay, which is Pc. So this is the minimum pressure required to liquefy a real gas at critical temperature. Okay, so minimum pressure required to liquefy a real gas at critical temperature. Critical temperature. Okay, now what will be critical volume then? Obviously volume occupied by mole of rather 1 mole of real gas at critical temperature. Critical temperature and pressure is called critical volume. So critical volume is nothing but Vc, that would be volume occupied by one mole of real gas at critical temperature and critical pressure. Now we'll be seeing critical constants. So we know that p plus an square upon, rather p plus a upon vm square and vm minus b is equals to rt. Now we can write that pvm square plus a into vm minus b would be equals to vm square into rt. Just multiplying the equation out. So vm cube minus pvm square, rather just having this like this, that pm square plus avm minus pbvm square minus ab minus vm square rt would be equals to 0. And from now on we can write that vm cube minus vm square b plus rt upon p plus a by pvm, this is capital P, vm minus ab by p would be equals to 0. So for this equation we can write that three roots are possible. Okay, so we can write that three roots for, let's say, vm minus v1, vm minus v2 and vm minus v3 equals to 0. So this can be simplified into this and can be written into something like this, because three roots are possible, and let those three roots be v1, v2 and v3. Okay, so at critical point what will happen is we would have so before that let's understand what would the nature of graph look like before getting to the critical point, or the values of vm v1, v2, v3 at the critical point. So we would have something like this graph, p and v here. So the nature of the graph would be something like at T1, let's say, which is lesser than the critical volume or critical temperature. So you would have something like so this is actually v1, or rather v1, v2 and v3. Okay, so we would have something like these three roots when we have rather 3 points of the conversion of gas into, from gas to liquid and gas phase, and from liquid and gas to liquid phase. So we would have three such volumes at which these 3 points would be occurring. Okay, so this would be simply called this graph would be when the real gas attains this graph or becomes a liquid, then it would be called super heated liquid. Okay, and for this graph it would be called as super saturated vapor. So obviously there would be many such graphs that would be many such graphs before the temperature becomes critical temperature. So at critical temperature, what would happen is we would have something like direct, means all the three phases, or all the two phases rather, would be indistinguishable. And if the all two phases becomes indistinguishable, means you are not able to distinguish between either a liquid phase or a gaseous phase, means all happens at a single point of volume. So that volume is we defined as critical volume, means the volume occupied by the real gas at critical temperature and pressure was the critical volume. So at critical volume, no distinguishing between, means all the two phases will not be distinguished, hence we won't be getting 3 points wherein the gas was first in a gaseous phase, then between liquid and gaseous phase, or supersaturated vapor, or in a superheated liquid. So we won't be getting these 3 volumes, we will be getting only one volume. Okay, that would be V critical. So at critical point we can write that all the 3 roots V1 equals to V2 equals to V3 becomes Vc, or critical volume. So in a way we can write that Vm minus Vc cube would be equals to 0. Okay, and the first equation which we saw was already this one. Okay, so now what will happen is at critical temperature and critical pressure and critical volume, this equation can be written as Vp, the pressure would be at C. Okay, and by combining both the equations we will be getting something like that. If we actually expand this equation, which is nothing but Vm minus Vc cube, will be getting something like Vm cube minus 3 Vc times Vm square plus 3 Vc square times Vm minus Vc cube equals to 0. And the first equation would look like Vm cube minus Vm square P plus R Tc upon Pc plus A upon Pc times Vm minus Av upon Pc would be 0. So just comparing these two equations, this equation is when Vm equals to Vc, we expanded the whole cube, and this was the original reduced form of the van der Waals equation. So just comparing these two equations, so from equation 1 and 2 you can write so by the way, before going into that, this can even be I'm just showing, just for the purpose of showing, a different root of V2 here, but this would be internally be joined here as well. So, okay, so this from let's say this point up till V3 temperature, it would be a gaseous phase. Okay, and from V3 to V2 it would be conversion, or having both phases, and then from V1 onwards it would be a purely a liquid phase. Okay, so I'm just showing this gap just to discriminate between V1, V2 and V3. I know that initially we drew actually only one graph, which was nothing but I think this was in the previous lecture or in the same lecture. I think liquefaction was in the same lecture, yes. So this was the original graph which we had drawn, in which I have not shown any difference between the conversion of liquid and gaseous phase and the liquid phase. We directly drew it, but just for showing the distinction of V1, V2 and V3, I showed a little bit of difference between conversion of real liquid and between liquid and gaseous phase. Okay, so this is just done for the sake of showing the discretion between V1, V2 and V3. Okay, so now for clarity purpose I have shown this, and also marked supersaturated vapor and superheated liquid in the respective phases. Okay, so now continuing on seeing the two equations, we can write that 3Vc would be equals to B plus RTC upon PC, and Vc would be equals to root of A upon 3PC, and from this two I wrote this one, from this two I wrote this one, and from these two I will be writing Vc cube would be equals to AB upon PC. So just simplifying all the three equations, we'll be getting something like from here we can get that direct let's not convert this into a square root, that's having a square here. So Vc cube divided by Vc square, so this is, let's say, third equation, and this is the fourth equation. So if we divide third by fourth, we will be getting Vc would be equals to AB upon PC divided by A upon 3PC. Okay, so PC and PC gets cutted out. This implies Vc would be equals to 3B. Okay, and just putting the value of PC here or in any of the equations, so we would be getting, let's put value of Vc in fourth equation, so we would be getting Vc square equals to A upon 3PC. So this implies PC would be equals to A upon 3Vc square. So this would give us PC as A upon 27B square. Okay, and similarly if we put the value of Vc, so let's suppose this was the fifth equation, Vc and PC in the fifth equation, we would be getting TCS. So this is for homework, this is the homework for you to derive the value of TC by putting Vc and PC value in the fifth equation. So we will be getting TC as 8A upon 27 RB. Okay, so we calculated three very important formulas at critical temperature, pressure and volume. What would be the value of a particular real gas? So at critical temperature, value would be 8A upon 27 RB or BR, whatever you want to say. Critical pressure would be A upon 27 B square, and Vc or critical volume would be 3B. Okay, so at these conditions, critical temperature, pressure and volume exist. Okay, and we can also say that this, at this value, we have calculated the temperature, volume and pressure. Okay, so this is the maximum temperature at which the liquefaction of real gas can take place. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more concepts on the law of corresponding states. So till then, good luck and goodbye.